Welcome to Part F of Unit 2 for our course on statistics. And we've been talking about the concept of sampling error. And now I want to use the concept of sampling error to introduce something called significance testing. And we're going to use significance testing to address the question of whether results from a research study could be explained by chance. Now, if you recall way back at the very beginning of this course, I talked about different questions we could address if we quantify our observations. And I said one important question we can address is whether results of a study can be explained by chance. And I said that would be a very important question that we would spend quite a bit of time in this class looking at ways that we can address that question. Now, note that the question of whether results of a study can be explained by chance, that's the same question as whether results of a study can be explained by sampling error. So recall the idea of sampling error. If I do a study and collect a sample of people and calculate a statistic, and then I could say what would happen hypothetically if I replicate my study and get a different sample of people and calculate that statistic, and then I replicate my study over and over and over again an infinite number of times. Each time I get a different sample and calculate my statistic. And each time I do my replication, I'll get a different value for that statistic. Some samples might produce a statistic that's high, and other samples might produce a statistic that's low. So there'll be fluctuations and variance differences between my samples in the statistics that they produce. And each statistic produced by a sample will likely be somewhat different from the true population parameter. So now we can ask the question, why is this true? Why do I get different statistics from different samples? Why does a statistic from a sample not equal exactly the true population parameter? Well, the answer is there's going to be random chance differences and fluctuations between samples. Each sample will be a little bit different from each other, and just random chance fluctuations and differences between the samples mean that each sample is going to produce a slightly different result. So, sampling error is error that's caused by random chance fluctuations and differences in samples. So, the question of whether results can be explained by chance is the same question as whether results can be explained by sampling error. Now, recall that we will address this question with something called an inferential statistic. And one way to use inferential statistics to address sampling error is to do something called significance testing. There are actually other options, other ways that we can address sampling error, but significance testing is certainly the most popular and most commonly used method for addressing sampling error. And as we will see, the process of significance testing will involve calculating something called a p-value. And what we're going to do is we're going to call results significant. We're going to label results as significant whenever our p-value is less than 0.05. So we'll say whenever p is less than 0.05, our results are significant. And on the screen is a bit of statistical humor you will only get if you understand significance testing. Because sometimes in romantic relationships, people might refer to their romantic partners as their significant other. Well, here I have painted p is less than 0.05 on this otter to make it my statistically significant otter. Well, actually I photoshopped it on there. I didn't actually paint the otter, but that is my statistically significant otter. So let's see how we can use the concept of sampling error to do significance testing. So what we're going to be doing here is that we're going to be doing some things with distributions of sampling error that are very similar to things we've already done with distributions of cases from a sample. And on the screen here I have pictures of two different types of distributions. And these are pictures you've seen before. These are illustrations I've used as we've been going through that googly-eyed sheep table talking about different types of distributions. And at the top is the very first distribution that we talked about when we talked about calculating just the basic standard deviation. And so this is a distribution of observations of what from what, observations of cases from a sample, deviations around what, looking at how far those cases deviate around the sample mean. So that's our distribution of cases from a sample, looking at how far those cases deviate around a sample mean. And then at the bottom, I have a distribution of sampling error, and I've got a bunch of X bars, a bunch of means in here. So this would be a sampling error of a mean that I'm depicting here. And so if we consider the questions on the googly-eyed sheep table for this bottom table, observations of what from what, it's observations of different samples from a population, or in this case I've got means, so it's an observation of different sample means from a population. And deviations around what? It's deviations around a population parameter. And the population parameter for a mean is mu. So I've got that mu down here. So looking at how far means from different studies deviate around the true population parameter. So I've got our two different distributions here, and recall that both of these distributions will have a standard deviation. For the top distribution, that we call that standard deviation, we just simply call it the standard deviation. And in the bottom distribution, if I have a distribution of sampling error, we call that distribution the standard error of our statistic. So if I'm looking at means here, that would be the standard error of the mean. So if both distributions have standard deviations, that means we could mark off both distributions in standard deviation units. And we've already done that with the top distribution of sample of cases from a sample. We can say that the mean right here, that's going to be 0. And if these cases are normally distributed, they might be or they might not be. But if they are, and a lot of times they are, if they are, then it would fit this normal shape. And we know that one standard deviation above the mean would occur right there, where I'm drawing that line there. Two standard deviations above the mean would be right there. One standard deviation below the mean would be right there. Two standard deviations below the mean would be right there. And then 3 would be here, and 3 above would be there. So if we have a distribution of cases and they fit the normal distribution, we know exactly where the standard deviation units will fall along that distribution, and we can mark our distribution off in standard deviation units. And we've done that before. Now, with our bottom distribution, in this case, we talked about the fact that sampling error will always be almost perfectly normal. So I don't really even have to say, well, maybe it might be normal, maybe it's not. We're just going to say it's always going to be normal. So sampling error will always fit this bell-shaped curve shape just exactly like this. And we can mark this distribution off. We can mark off our distribution of sampling error in standard deviation units. Or I should say more precisely, we're going to mark it off in standard error units. So right here at the population parameter, we'll call that 0. And then right here, this is going to be one standard deviation or one standard error above the true population parameter. And so we'll call that 1. And right here, where I've got this big black arrow, that's going to be 2 standard errors above the true population parameter. And up here, I'll draw a line up there. This is going to be 3 standard errors above the true population parameter. Or I could go down here. Here's going to be -1. That's 1 standard error below the true population parameter. Here's -2 standard errors below the population parameter. So just as we can, in our top distribution here, just as we can take a distribution of cases from a sample and mark it off in standard deviation units, with our bottom distribution, we can mark that off in standard error units. And in the top case, we know that sometimes our distribution might fit this normal shape, but for the bottom example here, we know it will essentially always fit that normal shape. So I could take someone from a study here. I've got this person in this top example. I have this person right here, this face up here, and I say, what if we take one person from this sample and her score on X is right here, right where I have this arrow? I would say, well, then she is 2 standard deviations above the sample mean. Now in this bottom example, say I do a study and I calculate the mean for my study, And the mean for my study, the x bar, the mean for my study is right here. So I could say the mean for that study is 2 standard errors higher than the true population parameter. So in both cases, I'm measuring things in standard deviation units, standard deviations in the top case, or officially standard errors in the bottom case. And so in the top example, I can take a single case from a sample and say, for this single case, how many standard deviations did this case score above the sample mean? And in the bottom case, I can take something out of this sample. In this case, it's going to be a sample. And I can take, here's a sample from this distribution of all the samples I would get if I replicate my study over and over and over again. Here's just one of the samples that I got when I replicated my study. And here's the mean I got from that particular sample. And I can say, for this particular sample, how many standard error units did this statistic fall above or below the true population parameter? So again, I get the statistic from my study and say, for this particular study, for this particular sample, how many standard error units did the statistic for this sample deviate above or below the true population parameter? And so what I'm talking about here is a process of standardizing our results, our mean or our statistic from a study. I could calculate a mean or a correlation or a beta weight or a mean difference. If I calculate a statistic for a study, can I standardize that study where I talk about how far that statistic deviated from the true population parameter in standard error units? And I have the question here, can we standardize? And as I'm leading to, the answer is going to be yes, we can standardize. And the next question is, well, why would this be useful? And so as we go along here, be thinking about this. I'm going to be talking about how we might be able to standardize a statistic from a study and talking about how far that statistic deviated from the true population parameter in standard error units. But as I'm going along here, I'm just going to raise this question, why is this going to be useful? So think about that as we go along. Why would this be a good thing to do? Now, let's review how we standardize scores from cases in a sample, and then use that to consider how we can standardize sampling error. So first, in the upper right-hand corner, I have the formula for a z-score, and this is just a review. You've seen that formula before. So with that formula, if we want to calculate the z-score for a person, we take the person's score on X, and we subtract from it the sample mean. That is, we center the person's score, and then we take that centered score and we divide it by the standard deviation, and that will produce a z-score. It would tell us how many standard deviations a person scored above or below the mean. And in our example here, I have this one person here, and I'm depicting her as having an X, a score on X of right here, and that score is 2 standard deviations. Here's the mean. There's 1 standard deviation. There's 2. She is 2 standard deviations higher than the mean, and so her z-score would be equal to 2. Now, note what we're doing with our formula here. I have a distribution of stuff, and I'm going to take one case out of that distribution. Say it's this case right here, and that's it, and I'll get her score on X. So this X right here is just one case that I pulled out of my distribution, and I'm going to subtract from that one case the midpoint of my distribution. The midpoint of a distribution of cases in a sample is the sample mean. So I take that single case, I subtract from it the midpoint of my distribution, and then I divide it by the standard deviation of my distribution, and that's what produces a z-score. Now, let's see how we could do the same thing if we're dealing with sampling error. So in our bottom picture here, I've got a picture of sampling error of a mean. That is, if I do a study, calculate a mean, get another sample, calculate the mean, replicate my study over and over an infinite number of times, get all the means from all my samples, and I have a distribution of sampling error, a distribution of all the means from all my replications. And so let's take this, I had this one study, this square right here, that's just one of my studies, and this particular study produced a mean that's right here. I have this X bar down here. And so if I want to standardize it, I will take I take this one thing out of this distribution. Now in the top example, if I take one thing out of my distribution, it's observations of what? Of cases in a sample. So if I take one thing out, I'm going to take out one case. In the bottom distribution, that's observations of samples in a population. So if I take out one thing here, I'm going to take out a sample. So this box here is just one sample that I pulled out of the entire distribution. And this sample had a mean. So I'm going to take the mean from my sample. That's one thing. I'm going to pull that one thing out of my distribution. In this case, I'm pulling out the mean from a sample. And then I'm going to subtract from that the midpoint of my distribution. In this case, the midpoint is the population parameter, and that's going to be mu. So we're doing the same thing here. I'm going to have a distribution of stuff, and I pull one case out of that distribution. In the top example, pulling one thing out of my distribution is to pull one case or one person or one individual out of my distribution. In the bottom example, we have a distribution of samples from a population, and so pulling one thing out of my bottom distribution is pulling out one sample. And that one sample will have a statistic. And it could be a mean, or it could be a correlation if we were looking at sampling error of a correlation, or it could be a beta weight if we were looking at sampling error of a beta. In this case, we're looking at the sampling error for a mean. So I have my sample, and my sample has a mean. So I pull one thing out of my distribution and get that value. In this case, it's the mean. And then I'm going to subtract from that the midpoint of my distribution. In this case, if I have a distribution of sampling error of a mean, the midpoint is mu, the true population parameter. So I pull one thing out of my distribution, subtract from it the midpoint, and then I'm going to divide that by the standard deviation of my distribution. So if I'm dealing with sampling error, or specifically sampling error of a mean, then the standard deviation of that distribution is the standard error of the mean. So I could standardize the sampling error for this particular study by taking the mean from that study, subtracting from it the true population parameter, and then dividing that by the standard error of the mean. And in the picture here, I'm showing the study that got a mean that was 2 standard deviations, or specifically 2 standard error units, higher than the true population parameter. So this bottom example, this particular sample would have a z-score of 2. Note that in our top example, I'm measuring how far this person deviated from the mean in typical deviation units. In our top example, a standard deviation tells us how far people typically deviate from the mean. And so if she got a z-score of 2, it means that her score is twice as far away from the mean as is typical. People typically deviated from the mean by 1 standard deviation, and she deviated twice as much. So in our top example, we're measuring how far people deviated from the mean in typical deviation units. In the bottom example, we're measuring how far studies deviate from a population parameter in typical error units. The standard error of the mean tells us what is the typical amount of error we would make in a study. On average, how far would study means typically deviate from the true population parameter? What's the typical error? And the typical error would be 1 standard error, and so this study made twice as much error as is typical. So its z-score would be 2. And on this page, I'm showing you some different versions of that z-score formula that we can use to standardize sampling error. In the upper left-hand corner is the exact same z-score formula that I showed you on the previous page. This is one we can use if we're looking at sampling error for a mean. And we saw how we could take the mean for a particular sample, subtract from that the true population parameter, and then divide that by the standard error of the mean. And that would produce a z-score for that sample or for that study, telling us how far the sample mean deviated from the true population parameter in standard error units. Now, like I mentioned, there's different types of sampling error for different statistics. We can have sampling error for a mean, we can have sampling error for a correlation, sampling error for a beta weight, sampling error for a mean difference. And what I've done to the right here is I've written this exact same formula, but I've used more general terms so that it could apply to be used for any type of statistic. And the general version is we take our statistic, whether that's a mean or a correlation or a beta weight or whatever it is, and we subtract from that statistic a true population parameter, and then we divide that by the standard error of that statistic. And so our statistic is the statistic we draw from a sample. And so we take our sample statistic minus the true population parameter divided by the standard error of the statistic. So for example, we could take a correlation minus the true population parameter, which would be the Greek rho symbol, divided by the standard error, would be the standard error of the correlation. Or we could take a beta weight minus the true population parameter divided by the standard error of a beta and get a z that way. So this formula in the upper right is the general formula you can use with any statistic. Now, as we're working with this, note that this numerator, statistic minus parameter, that's essentially calculating how much error was made in a study, how far a particular study deviated from the true population parameter. So statistic minus parameter is the same thing as calculating the amount of error that was made in a study. And note that the standard error of a statistic, that's the typical amount of error, the average amount of error that's made across studies. So we could say that's the expected or likely error in a study. So another way to think about what we're doing with the z-score formula is we're taking the error that we have in a particular study and dividing it by the expected error that we would have. So different ways of considering what that z-score formula is doing. Now recall that I mentioned that a distribution of sampling error will always nearly perfectly fit the shape of a normal distribution. That means when we're dealing with sampling error, we could always use a normal distribution to determine probabilities. On the screen, I have a picture of a normal distribution, and note that I have the probabilities down here, that the ones you've already memorized for different areas under the curve. So we've memorized that, for example, if you have a 0.1 standard deviation above the mean on a normal distribution, that 16% of the cases fall above that point and 84% fall below that point. Or if you have a point here is 2 standard deviations above the mean, we know that 2% of the cases will be above that point and 98% of the cases will be below that point. So if we were to use this formula to calculate a z-statistic for sampling error in a study, for example, say we do a study and calculate the mean, and on the picture here I've got all these x bars, all these means in my sample, so we're looking at a distribution of sampling error of means. And so if I do my one study and get the mean from my study, subtract from it the true population parameter, divide it by the standard error of the mean, and I get the z value for my study, that if I calculate a z value for my study, I know the probability of making more error than that and the probability of making less error than that. If I get a z value that's right here, say my z is 1 standard deviation above the true population parameter, that is, if the statistic from my study is 1 standard error unit higher than the true population parameter, well, I know the probability of making more error than that is 16%. Let's plug in the example we've been looking at. And the example that we've been considering is a situation where I collect a sample of people and calculate the mean for that sample, and the mean for my study is 2 standard errors higher than the true population parameter. And we saw how the z-score, if I calculate a z-score for that study, my z-score would be 2, because that study is 2 standard errors higher than the true population parameter. This would mean that this study made twice more error than is typical. So 1 standard error is the typical amount of error. That's how far sample means typically deviate from the true population parameter. And so if a study was just 1 standard error higher than the true population parameter, then that study would make the typical amount of error. This study, my study here, that's 2 standard errors away from that true population parameter, because it's 2 standard errors away, it means that study made twice more error than is typical. Now, like I was saying, we can then use the z-score. If the study has a z-score of 2, we could use that z-score to determine probabilities, because we know that if you are 2 standard deviations away from the midpoint of a normal distribution, that only 2% of the area under the curve is higher than that point. In other words, if I replicate my study over and over and over again, only 2% of the time will I get a z-score higher than positive 2. And I also know that only 2% of the time will I get a z-score lower than negative 2. So if I am 2 standard errors away from the true population parameter, I will know I will only make that much error 4% of the time. So 2% of the time I might be higher than 2 standard errors away from the true population parameter. 2% of the time I might be lower than negative 2 standard errors away from the true population parameter. In either direction, how often will I get a score this extreme? How often will I do a study and calculate a mean and have my mean be more than 2 standard errors away from the true population parameter? That is, in either direction. And we can look it up on a normal unit table and determine that, well, the probability of that is 4%. That will only happen 4% of the time or less will you do a study and get a mean that's more than 2 standard errors away from the true population parameter. And I'm going to symbolize that. I'll use the letter P to indicate probability. So I'm going to say the probability of getting scores that are more extreme than 2 standard errors away from the true population parameter is less than 0.04. It happens less than 4% of the time. So I'll say for a z-score equal to 2, the probability is less than 0.04. In other words, this is a very rare event. So now if we go back to that question, why would we want to calculate z-scores? Why would we want to standardize our sampling error? Well, it will help us understand, are the results from our study typical results or very unusual, rare results? If I do a study and calculate a mean, it might be helpful to know, is this mean that I got, is this an outlier? Am I way, way out here? Is this a highly improbable, unusual mean that I got from my study? Or maybe I calculate a mean and my mean is right here, very, very close to the true population parameter. That would be a typical normal type of outcome that I would expect. So it might be really useful to know, if I do a study and calculate a statistic, is my statistic that I just calculated, is that a highly improbable, unusual, rare event? Or did I get a typical expected statistic for my study? Did I get a statistic that comes maybe pretty close to the true population parameter that's in the range of what I might expect? Or did I get something that's rare and weird and unusual? And this would be a very useful, good thing to know. Now, I've been talking about how wonderful and fabulous it would be if we could calculate a z-score to indicate the standardized amount of sampling error for a statistic from a study. And hopefully I've convinced you that this would be a good thing to do. And maybe you're even thinking to yourself right now, yes, this sounds great. I really, really want to be able to do this. I want to be able to calculate a z-score to indicate the standardized amount of sampling error for a study. But maybe along the way, you might also have noticed one little tiny problem in what I've been talking about. And the problem is this. Well, I've been talking about something that would be impossible to do. We can't do it. So here's the formula that I have for the z-score for a mean. If I'm doing a study and I calculate the mean and I want to standardize the sampling error for the mean, so I take the mean for my study, that is, it's the statistic for my study, and I subtract from it the true population parameter, and then I divide it by the standard error of my statistic. In this case, it would be the standard error of the mean. And the problem is, well, there's a couple problems. The first problem is we don't know what the true population parameter is, and we can't know what the true population parameter is. And if we did know what the true population parameter was, there'd be no point in doing my study in the first place. The whole reason for doing a study is because I don't know what the population parameter is, and I want to try to get a good guess what it is. And so I do my study, and I collect a sample of cases, and I calculate the mean for my study because I'm trying to estimate what I think the true population parameter is. And if I knew what the true population parameter was, there would be no point to doing my study in the first place. And the whole reason why we're doing statistics is because we can't know what these true population parameters are. So I can't simply plug in the true population parameter because I don't know what it is. And the other problem is down here. If I say I'm going to divide by the standard error of my statistic, well, that standard error is what I get if I replicate my study over and over and over again an infinite number of times and then calculate the standard deviation of that distribution. And I can't do that. I can't replicate my study an infinite number of times and calculate the standard error of my statistic. That's another type of population parameter. It's the population standard error. It describes that standard error in the entire population, and I can't know what that is. So I don't know what the true population parameter is, and I don't know what the true standard error of my statistic is. And so how can I use this formula? Well, there are a few tricks we can use. There's a few things we can do to actually solve this problem. You might even see, I wonder if you could guess what we could do to solve this problem before I tell you what it is. So let's look and let's see how we can solve this problem. Let's see, because hopefully everyone is thinking right now, yes, we really want to use this formula. We want to be able to calculate this. We want to be able to calculate this z statistic, where we take the statistic from our study, subtract from it the true population parameter, divide it by the standard error of our statistic. We want to be able to do that, but how can we do that when we don't know the true population parameter and we don't know the standard error of our statistic? Well, let's take a look and see. First, let's deal with the issue that we don't know what the standard error of our statistic is. That is, we can't replicate our study over and over and over again an infinite number of times and then calculate the standard deviation of that distribution. So what can we do? Well, as it turns out, I've got some good news and some bad news for you. The good news is we can actually use information from our sample and estimate what this standard error is. We can estimate it using information from our sample. And what information do we use from our sample? Well, recall that I mentioned that the standard error of a statistic is primarily determined by your sample size. When you have a big sample, your standard error of your statistic will be really small. And when you have a really small sample, your standard error of your statistic will be very big. So your standard error is determined primarily by sample size. And we have formulas that we can use where we can take the size of a sample and plug them into the formula and estimate the standard error of a statistic. As it turns out, we'll have different formulas for each different type of statistic. For example, there's one formula for the standard error of a correlation and a different formula for the standard error of a mean. And we'll be looking at those formulas later on as we go through this course. So the good news is we have formulas that we can use where we take the size of our sample, plug them into our formula, and estimate what the standard error of our statistic is. So if that's the good news, what's the bad news? Well, the bad news is this, because if we were to take and estimate the standard error from our using information from our sample, that estimate isn't exactly perfect. It's going to be a little bit off. And what that means is that the shape of this z distribution will no longer be normal. That is, one of the things I was talking about just a moment ago was the fact that the distribution of sampling error will always nearly perfectly take on this normal shape. And so if we calculate z-scores and know where a study falls along this normal distribution, we know the exact probabilities of studies being higher or lower than that point. And so we had this study here that was 2 standard errors away from the true population parameter, and we know that would only happen 4% of the time or less. That would be higher than positive 2 standard errors or lower than negative 2 standard errors. 2 standard errors more extreme away from the true population parameter, that only happens 4% of the time or less. And so we could say the probability of that is less than 0.04. And so these z-scores were very useful for we could use them to determine probabilities because we knew the shape of our sampling error would be normally distributed. But once we use our sample to estimate our standard error, that's no longer true. The shape is no longer normal, and we can't use the normal distribution to estimate probabilities. So at this point, you may be feeling pretty deflated and discouraged about that news. But before you get too discouraged, I actually have some more good news for you, because although our shape of our distribution will no longer be normal, it will actually be a different shape that also can be defined by a mathematical formula. It's no longer a normal distribution, it's a different distribution, and it's a different distribution that's defined by a mathematical formula, so we can actually still determine probabilities. So what is this other distribution? We call it a t-distribution. That's lowercase t, not to be confused with the uppercase t that is used to talk about a t-score, which is a type of standardized score with a mean of 50, standard deviation of 10. I'm talking about something different here. This is a lowercase t, and this is used to indicate a t-distribution, and it's the shape our distribution will take on if we estimate our standard error using those formulas that we have, where we can estimate our standard error using our sample size. So if we use our standard error, if that's estimated from our sample size, then I have, note these two formulas are the exact same formula. On the right, I call it a z formula. On the left, I call it a t formula. And they're the exact same formulas, except for one thing. On the right-hand side, I'm saying this is the actual true population standard error. It's the real thing. It's what we would get if we replicated our study over and over an infinite number of times and calculated the real standard error. And on the left, it's the standard error that's estimated from a sample. It's the standard error we get if we estimate it from a sample. And if we estimate our standard error from our sample, we'll no longer call this a z-score, we'll call it a t-score. And we call it a t-score because now if we estimate our sampling error, if we standardize it using this formula, that it will fit a shape, but it's no longer a normal distribution shape. It's the shape of this thing we will call a t-distribution. So if we estimate our standard error from our sample, we calculate this t-value, and our standard errors will fit this distribution that's a shape of a t-distribution. Now, let's take a moment to clarify just exactly what I've been talking about. So, on the screen, you see that picture that I've been showing you all along to illustrate a distribution of sampling error. Or specifically, this is a distribution of sampling error for a mean. That is, if I do a study, get a sample of people, and calculate the mean for that sample, and then I replicate my study over and over and over again an infinite number of times, and then I get all the means from all those samples from all my replications, the distribution of all those means is my distribution of sampling error, and that's what we're looking at on the screen. So each one of these x bars under this normal curve, I'm going through here, I'm circling some of these x bars. Each one of these x bars is a mean from a different sample from one of my replications. So I have all these means from all my replications. Now, let's consider this z formula in the upper right-hand corner. This is something I could take a mean from a single study and standardize it using this z-score. So for example, I'll circle one of these x bars. Say I take this sample, this study right here, produced this mean right here. I could take the mean from this study and plug it into my formula up here. I'll take that mean, subtract from it the true population parameter, divide it by the standard error of the mean, and that'll produce a z-score. And that would transform that mean. That mean would then become, scribble that out, put a z here, to become a z-score. I transformed my mean into a z-score. Now I could do that for every single mean in this distribution. I'll put some z's on top, so not sure if you can see very well. I'm putting z's on top of my x bars. I'm putting z's on top of these means. So if I go through and I convert each one of these x bars, each one of these means, I'm converting it into a z-score. So I take each one of these means and I standardize it. I use this formula up here and I turn my mean into a z-score. Now, if I do that, the shape of this distribution will not change. I'll still have the exact same shape. This is the same thing that's true when we turned scores for people into z-scores. When we standardized scores for people in a sample, when we turned people scores into z-scores, that changed the scale, but it didn't change the shape of the distribution. So, and the same thing is true here. We'll still have exactly the same shape of this distribution of sampling error. The thing that changes when we convert scores into z-scores is the scale along the bottom. Because when we convert scores to z-scores, it means that we now have a distribution where the midpoint right here, that's the true population parameter, and that midpoint is going to be 0 on our scale. And one standard error, or one standard deviation, one standard error higher than that midpoint is going to be a score of 1 on our scale. And if you're 2 standard errors higher than that midpoint, it's going to be a score of 2. So when we plug in this formula for a z-score, we change the scale along the bottom so that 0, the true population, is the true population parameter, the midpoint of the distribution. The true population parameter is 0. And we take each sample and indicate how far that sample scored above or below that true population parameter in standard error units. So we've changed the scale, but we haven't changed the shape of the distribution. So what I've been saying with the t-score, though, is that if I use this standardization formula and I don't have the real standard error of my statistic, and so I estimate it based on my sample size, if I do that, let's make that transformation. And this time, I'm going to say instead of a z, I'm going to call that t. I call it t because I don't have the real standard error of my statistic. I'm estimating it based on my sample size. And so I take, say, let's take the mean from this study right here. I'll circle this x bar here. I'm going to take that mean minus the true population parameter and divide it by my estimated standard error of the mean based on my sample size, my estimated standard error, and I'll convert that x bar into a t-score. And then I'll do that for every single one of these x bars, every single one of these means in my distribution. So I'm going to turn each one of these means into a t-score. And the reason why I'm calling this a t-score and not a z-score is because when I do this, this will change the shape of the distribution. It will no longer come so neatly, perfectly close to this normal distribution. It'll be something a little bit different. It's no longer going to be a normal distribution. It'll take on a different shape. So if I use my estimated standard errors based on my sample size and plug it into this standardization formula, and I convert all my means from my studies, if I convert them all into standardized values using that formula, I'm going to get something that will no longer fit that normal shape. It's a different shape, but it is a known shape. It's a shape that's defined by a mathematical formula. So we know what that shape is, and we can still determine probabilities. It's just no longer a normal shape, and we call that shape a t-distribution shape. The t-distribution is the shape we get when we standardized our sampling error from all of our statistics, from all of our studies, from all of our replications. If we standardize our sampling error, but we don't know the real true standard error of our statistic, and instead we estimate that standard error using our sample size, then that will result in a distribution that takes on the shape that we call the t-distribution. So the t-distribution is the shape of the distribution that we get if we use this formula to standardize the sampling error for a statistic, and if when we use this formula we don't know the actual standard error of our statistic, and that will always be true. We will never know that. So if we don't know the standard error of our statistic, we can estimate that standard error using our sample size. And we can take the size of our sample, plug that into one of the formulas that I'll be giving you later on, and use that to estimate our standard error. But when we estimate our standard error using our sample size, the shape of this distribution will no longer be a normal distribution. It will take on the shape of a t-distribution. And just like a normal distribution, the t-distribution is defined by a mathematical formula, so we can use a t-distribution to look up probabilities and determine probabilities of scores. So if a t-distribution is a different shape from a normal distribution, what exactly is its shape? Well, actually, a t-distribution will have many shapes. The t-distribution is actually a family of distributions, and it changes shape slightly depending on your sample size. If you have a larger sample, it will be one shape, and if you have a smaller sample, it will be a slightly different shape. Or more precisely, actually what it is the t-distribution changes shape depending on your degrees of freedom. So if you have a large degrees of freedom, it will look one way. Smaller degrees of freedom, it will be different. Now, if you have a very large sample and therefore a large degrees of freedom, your t-distribution will actually be very, very similar to a normal distribution. In fact, if your sample size is, say, more than 100 people, at that point the t-distribution actually becomes indistinguishable from a normal distribution. It's almost identical. But as your sample size gets smaller, as your degrees of freedom get smaller, the t-distribution gets flatter and wider. It's kind of like you can imagine someone putting their thumb on the top of this distribution and pointing down right with that arrow to kind of squish it out a bit. If I could draw, I'm going to draw a couple lines here. This is kind of like squished out. It's a little bit wider and a little bit flatter. So as your sample size gets smaller, as your degrees of freedom get smaller, the t-distribution becomes somewhat flatter and wider. So I have here the t-distribution has slightly flatter and wider when your sample size is small, that is when your degrees of freedom are small, and it's the same, well, it's actually not identical, but it comes infinitely closer and closer and closer to a z-distribution when your sample size is large. So that's what a t-distribution is, and that solves that issue, that whole problem we had is we wanted to use this formula to standardize our sampling error for a statistic. Recall that was where we started. I said we really want to use this formula. We want to be able to plug this in and to calculate a standardized sampling error for our study, but we couldn't do that because we didn't know the actual standard error of our statistic. And now I've solved that problem. We can plug in an estimated standard error, and it changes our shape from a z to a t, but we can still use that because t is a mathematically defined formula, and so that solves that problem. But you might be thinking, wait a minute, there's still one more problem we need to solve. So as the little kitty cat here says, okay, but what about mu? What about mu? We still have that problem, our population parameter. So in the formula to standardize our sampling error, I say we take our statistic, we subtract from it the true population parameter, and then we divide that by the standard error of our statistic. And I've just solved the problem about the fact that we don't know what the true standard error of our statistic is. I said we can estimate that using our sample, and that changes our statistic from a z to a t. So we've solved that problem. But what about the problem that we don't know what the true population parameter is? If our statistic is a mean, that true population parameter is mu. So if we don't know the true population parameter, how can we use this formula? What's our solution to solve that problem? Well, my solution to that problem is going to be something quite simple. Let's just do this. Let's just make an assumption. Specifically, let's assume that the true population parameter is 0. And if we just assume that the true population parameter is 0, we can then plug that into our formula and calculate our t-value. So on top here, I have the t formula if we're dealing with a sample mean. And so we could take the mean from our sample, x bar, and subtract from it the true population parameter, which we're simply going to assume is equal to 0. And then we can divide that by the standard error of the mean, which we estimate based on our sample size. And voila, there we go. We can calculate our t-value. Or at the bottom, I have the more general version of the t formula. And it goes like this. We get the statistic from our sample. We get a sample of cases and calculate a statistic, which could be a mean or a correlation or a beta weight or a mean difference. We calculate our statistic. We subtract from that statistic a true population parameter, which we're just going to assume is equal to 0. And then we divide that by the standard error of our statistic, which we estimate based on our sample. And there we have it. We have a t-value. And what do we call this assumption I'm making here? If I assume the true population parameter is 0, what do we call that assumption? Well, we call that the null hypothesis. The null hypothesis, N-U-L-L, the null hypothesis is the hypothesis that the true population parameter is equal to 0. And it's somewhat of an odd hypothesis to have if I'm looking at a sample mean. For example, if I'm looking at, say, how much people like blue-footed booby birds, it would be kind of odd to say on whatever scale I have, I'm assuming the sample mean is 0. But some of the other statistics we'll be looking at, the null hypothesis will be much more meaningful. So if I'm looking at a difference between two means, the null hypothesis is that the difference between means is 0, that there's no effect. There's no difference between the groups, that both groups are the same as each other. So in that case, if I'm looking at a difference between means, the null hypothesis is that that difference is 0 and there's no effect. Or if I'm looking at a correlation, the null hypothesis is that the correlation is 0, that there's no effect. Or if we're doing regression and calculating beta weights, our null hypothesis would be that the beta weight is 0, and like a correlation, that would also indicate that there's no effect. So usually the null hypothesis is an assumption that there's no effect, that the effect we're looking at is absolutely 0. That's the null hypothesis, and we're simply going to assume the null hypothesis is true, and once we assume the null hypothesis is true, we can calculate our t-value, and there we go. Now, you might be wondering at this point, why would we want to do this? Why would we ever want to assume the null hypothesis is true? Well, if we assume the null hypothesis is true, that allows us to calculate a t-value, and then we can make a statement about our study under the assumption of the null hypothesis. We can make a statement that goes something like this. If the null hypothesis is true, here's something important to know about our study. Now that first part will be important. We will have to preface our statement by saying, if the null hypothesis is true, here's something to know about my results. So, for example, say I do a study and I calculate a mean. I get a sample of people and calculate a mean, and then I use the size of my sample to estimate the standard error of the mean, and then I plug these values into my t formula here. I take the mean from my sample, subtract from it the true population parameter, which I simply assume is 0, and then I divide that by the standard error of the mean that I estimated, and I would get a t-value. And for example, say I do that and I get a t-value that's equal to 2. Well, then I could say something like this. If the null hypothesis is true, again, that's an important preface, if the null hypothesis is true and I got a t-value of 2 under that assumption, that means this study made twice the typical error, which is quite a bit of error. If the null hypothesis is true, then this study made twice the typical error. Also, just as we could calculate a z-score and look up probabilities of z-score using the normal table, once we calculate a t-score, remember that a t-distribution is also a distribution that's defined by a mathematical formula, so we can look up probabilities of t-values. And if I had a very large sample, the probability of a t-value would be very similar to the probability under a normal distribution of a z-score. So say, for example, I calculate my t-value and get a t-value of 2, I could look up and determine how probable is it to get a t-value of 2 or more extreme. How often does that happen? And depending on the size of my sample, it could give me slightly different results. Say I do that and discover that the probability is 0.04 or smaller. So if I do that, I could say, if the null hypothesis is true, I looked at the probability of this t-value of 2, and that probability was 0.04. That means the probability of making this much error is less than 0.04. It would only happen 4% of the time or less would I do a study and make this much error. So that means that if the null hypothesis is true, this is a highly improbable result. It would only happen 4% of the time or less that I would do a study and make this much error. I've made a tremendous improbable amount of error in this study, importantly, if the null hypothesis is true. So in this situation, I might say, well, now I think I'm going to question whether that null hypothesis is true. If I do a study and I assume the null hypothesis is true, and under the assumption of the null hypothesis, get a t-value that tells me if the null hypothesis is true, I've made twice the typical amount of error, and the probability of making this much error is 4% or less, a very improbable result. Well, now I might start to question whether that null hypothesis really is true. And I might think, well, maybe I should reject that null hypothesis. Now, notice what is happening to our formula for a t-value if we assume that the null hypothesis is true. So up at the top, I have the general formula for a t-value, the one I showed you before, where I said we take a statistic, and this could be a mean, or it could be a mean difference, or it could be a correlation, or it could be a beta weight. We take a statistic from a sample, and then we subtract from that the true population parameter, and then we divide that by the estimated standard error of that statistic. Now, if we're going to assume that the null hypothesis is true, if we're going to assume that the true population parameter is 0, well, then our formula becomes the formula I have in the middle of the page. A t-value is equal to a statistic minus 0 divided by the estimated standard error of that statistic. And of course, that will simplify. That simplifies to what I have at the very bottom of the page is a statistic divided by its standard error, a statistic divided by the standard error of that statistic. And we're going to be working with t-values at several points throughout this course. And every time we do, the formula will always be the same thing. It will always be a statistic. Now, we'll be looking at different types of t-values, like for a correlation or a mean difference or a beta weight. But in every single case, it will always be this, a statistic divided by the standard error of a statistic. So this is one thing that will be very helpful if you get this down really well. What I have in the black box here, a t-value is always calculated as a statistic divided by its standard error. And to reinforce that point, I have a song about the t-value, and the lyrics simply state, a t-value is always where you divide a statistic by its standard error, or you divide a stat by its standard error. So this gives the basic definition of the formula for a t-value. And it's important to have this down well because we're going to be using this frequently throughout this course. And the lyrics to this song are quite short, so certainly you should be able to sing along with this song without looking at the words well before it's over. So here is the song, The T-Value. So now that you know what a t-value is, we can talk about how we can use a t-value to do significance testing. And significance testing can be described as involving 3 steps. And so the first step, step 1, is simply to assume the null hypothesis is true. So whatever statistic we might be planning to calculate in our study, we're just going to assume that in the population the value is 0, that the true parameter is equal to 0. And we can write out our null hypothesis as you see at the bottom of the screen. So for example, here I have capital H subscript 0. That stands for the null hypothesis. That's the symbol for the null hypothesis. So the null hypothesis, if I'm going to calculate just a single mean for a sample, is that in the population, the true parameter, that's mu, the Greek letter mu, is the population parameter for a mean, that mu is equal to 0, that the population mean is 0. Or if I was going to do a study and I was going to calculate a mean difference, that is, maybe I had a treatment group and a control group, and I was going to see if there was a difference between those two groups on some outcome variable, well, in that case, my null hypothesis is that there's no difference between groups in the population, that mu for group 1 minus mu for group 2, that's the difference between the two means in the population, that the difference between means in the population is equal to 0. That is, the null hypothesis is that the population mean difference is 0, that there's no effect, no difference between groups whatsoever. That's the null hypothesis. Or if I was doing a study and I was planning to calculate a correlation, well then my null hypothesis is that in the population the true parameter is 0, and the population parameter for a correlation, we use the Greek letter rho to symbolize the correlation population parameter, and so rho is equal to 0. The true population parameter is equal to 0. The population correlation is equal to 0. That's the null hypothesis. Again, it's the hypothesis that there's no effect, no correlation, nothing going on, no relationship between variables whatsoever. Or if I'm doing a study and calculating regression and a beta weight, my null hypothesis for the beta is that in the population, the true parameter, the population beta, is equal to 0. That is, the population beta is 0. Again, it's the hypothesis that there's no effect whatsoever. And that's the very first step, is we simply assume the null hypothesis is true, and that's where we start when we do significance testing. Then, after we assume the null hypothesis is true, we're ready to proceed to the second step of significance testing. And in step 2, this is where we're actually going to run our study and collect data. So we do our study, we collect data, and then we calculate something that I'm going to call a test statistic. And a test statistic is a statistic that has a known distribution if the null hypothesis is true. It's something that has a known distribution if the null hypothesis is true, which means if we calculate a test statistic, we can determine the probability of that statistic under the assumption of the null hypothesis. And that's exactly what the t-value does. That's what we've been talking about with the t-test, or the t-value. Now, in a moment, I'm going to tell you about a couple other types of statistics that we can use that will be test statistics. The t-value isn't the only statistic that has a known distribution if the null hypothesis is true. There's a couple others we can use as well, and I'll talk about those in a moment. But for example, we could calculate a t-value, and a t-value would be a test statistic because it has a known distribution if the null hypothesis is true. And we've been looking at how we can do that. We get the statistic from our study, for example, the correlation or the mean or the difference between means, the mean difference or beta weight. We get the statistic from our study, subtract from it the true population parameter, which we assume is 0, divide that by the estimated standard error of our statistic, and we have our t-value. In other words, our statistic divided by its standard error gives us a t-value, and once we have a t-value, we can determine its probability, which is leading us to the next step. Then, once I have calculated a value for my test statistic, the third step in doing significance testing is to determine the probability of that test statistic under the assumption that the null hypothesis is true. So for example, if my test statistic is a t-value, I could calculate my t-value for my study, and then I would determine the probability of that t-value if the null hypothesis is true. And I can do that because the t-distribution is a distribution that has a known shape if the null hypothesis is true. And the process is just like what we did when we looked up probabilities of z-scores. With z-scores, we used the normal distribution, and the normal distribution was defined by a mathematical formula, and once we knew a z-score, we could determine the probability of that z-score by looking it up on a table or using a z-score calculator or using statistical software. We can do the same thing with t-scores because the t-distribution is also defined by a mathematical formula. So once we have a t-value, we can look up that probability of that t-value. We can use there's t-tables, there's t-score calculators that would give us probabilities, or we can use software programs, statistical software, to get the probabilities of our t-values. Now, one little difference is that when we're determining probabilities of t-values, we also need to know our sample size, or our degrees of freedom. Recall I mentioned that the t-distribution changes shape just slightly depending on your sample size, or your degrees of freedom, more precisely. So depending on your degrees of freedom, your probability when you look it up will be slightly different. If I have a t-value of 2 based on a sample of, say, 100 people, the probability will be a little bit different than if I had a sample of 30 people. But say, for example, I look up the probability of my t-value. Say I get a t-value of 2, and I look up the probability of that t-value, and my probability is 0.04. That would mean that the probability of getting a t-value this extreme, if the null hypothesis was true, is 4% or less. It would be a fairly rare occurrence. I would only get a t-value this extreme 4% of the time or less if the null hypothesis were true. That's what a p-value of 0.04 means. And so once I calculate the p-value, that is the probability of my test statistic under the assumption of the null hypothesis, once I calculate that p-value, I'm going to use that p-value to make a decision. And that decision is going to be a dichotomous decision between two options. One option is to fail to reject the null hypothesis. With that option, I simply decide that I don't have any evidence to make any claims about anything, that my results were inconclusive, and my study didn't find anything. The other option is to reject the null hypothesis, and that's where I say my study had results and I can make a claim about something. I can make a claim to have discovered some non-zero effect, and I'm going to reject that null hypothesis and claim that my study has found some non-zero effect. If I fail to reject the null hypothesis, I'm going to label that as non-significant. If I reject the null hypothesis and claim to have discovered something, I'm going to call that significant. So significance simply means that I have calculated a test statistic and calculated the probability of that test statistic, and based on that probability have come to the conclusion that I'm going to reject the null hypothesis and claim to have discovered some non-zero effect. That's what significance means. So to make this decision, we need some kind of guideline, and we essentially need some kind of arbitrary cutoff that we can use. And what we're going to use is a cutoff of 0.05, and we're going to call this cutoff alpha. And I have the Greek letter alpha here. Now, before I talked about reliability and something called Cronbach's alpha, and that was the same Greek alpha letter, but that means something completely different. We're talking about something completely different here. We're going to use this alpha to mean this is going to be the cutoff we're going to use for making decisions about whether or not we can call something significant or not. And so alpha is going to be an arbitrary cutoff. There's no rhyme or reason to it. It's just an arbitrary cutoff. But it turns out that researchers have selected a cutoff and they've stuck to it for many, many years. So we actually have a well-established arbitrary cutoff. Simply by tradition, this is what researchers almost always use, is a cutoff of 0.05. So what this means is you need to get a p-value that's smaller than 0.05 to call something significant. If your p-value is not smaller than 0.05, you say, well, this is within normal limits of what might occur if the null hypothesis is true, therefore I'm going to fail to reject the null hypothesis and call my result significant. So alpha, this is the cutoff we use for determining if results are significant or not. When we calculate our p-value, if our p-value is smaller than alpha, it means results are significant. If our p-value is not smaller than alpha, it means our results are not significant. So that's our third step. We determine the probability of our test statistic, assuming the null hypothesis is true, and then we make a decision. And we make that decision based on our probability. If our probability is less than 0.05, we say we've got results that are so improbable, it's highly unlikely to get a t-value this extreme if the null hypothesis is true. Therefore, we're going to reject the null hypothesis and claim to have discovered something in our research study. If our p-value is not less than 0.05, if I got a p-value, say, of 0.8, I'd say, well, that's not less than 0.05, and so I'm going to say, well, I'm going to fail to reject my null hypothesis. I'm going to say these results are within normal limits or within reasonable limits of what might occur if the null hypothesis is true. This isn't sufficient evidence to reject the null hypothesis. Therefore, I'm going to fail to reject the null hypothesis, and I'm going to refrain from making any claims to have discovered something. And I will be very sad to have conducted my research and not discovered anything, but that's the way it goes. And this slide summarizes this decision that we make when we're doing significance testing. So on the left, I have if your probability is greater than 0.05. If your probability is greater than 0.05, that's where you say results are not significant and you fail to reject the null hypothesis. That means you simply continue to assume the null hypothesis is true. Recall, that's where we started. I said we start the whole process of significance testing by merely assuming the null hypothesis is true. And so if we fail to reject the null hypothesis, it simply means we're just not going to change our assumptions. We started off just assuming the null hypothesis is true. Our study didn't give us sufficient reason to reject that null hypothesis. So we're simply going to continue assuming the null hypothesis is true. In other words, if we say our results are non-significant and we fail to reject the null hypothesis, we're essentially saying our results are inconclusive. It's possible that our results might be a mere chance fluke finding. Recall that we're doing significance testing to address that question. Could these results be explained by chance? And when we fail to reject the null hypothesis, when we say our results are non-significant, we're saying, well, yeah, the results might be simply caused by chance. We don't know, but it's possible we've got results here that are simply a random fluke. It's possible our results might simply be a random chance, and so we really can't claim anything. So if we fail to reject the null hypothesis, now note that we're not saying that we think the null hypothesis is true. We're just saying we weren't able to claim anything. So saying results are non-significant means we're not going to claim anything. And at this point, if I calculated an effect size, like a D statistic or a correlation or something like that, I wouldn't try to interpret. I would just simply ignore that. I'd say I don't have any evidence there's any effect at all. So I wouldn't talk about, well, do I have a large effect or a small effect or a medium effect? Is my correlation large, small, or medium? Or is my D statistic large, small, or medium? I wouldn't interpret my effect size because if I fail to reject the null hypothesis, I don't have any evidence that I can claim any effect at all. So I'm not going to make comments that might interpret my effect size. I'm going to essentially ignore the effect size because I don't have any evidence that it's giving me anything meaningful. In contrast, if my p-value is less than 0.05, that's where I would have significant results. So I call my results significant if the p-value is less than 0.05. That means these results would be highly improbable if the null hypothesis were true. And because I got results that would be highly improbable if the null hypothesis is true, I'm therefore going to reject that null hypothesis. The null hypothesis is that the effect is 0, so I'm going to reject that hypothesis and claim that the effect is non-zero. So I reject the null hypothesis and claim to have discovered some non-zero effect. Now note, at this point, when I'm doing significance testing, I'm not making any claims about how big the effect is. I'm just claiming that the effect is not 0, and nothing more than that. That's all I'm claiming. I'm just claiming I have discovered some non-zero effect. Now, when my results are significant and I claim to have discovered some non-zero effect, we can interpret that as a license to go ahead and interpret the effect size. So I could look at a d-statistic or a correlation or some measure of effect size and say, well, how big is my effect? And go on to address the question of effect size. So the significance test in and of itself does not tell me anything about effect size, but once I get a significant result, it's kind of like a license that allows me to go ahead and interpret my effect size. So the significance test, though, simply allows, if I say results are significant, it simply allows me to claim to have discovered some non-zero effect. So that's the decision we're making when we do a significance test. Now, one very important thing to keep in mind here is the fact that significance is largely determined by the size of your sample. To a large extent, significance is determined by sample size. Let's look at our formula for a t-value and see how this is true. So recall that a t-value is always calculated where we take a statistic and divide the statistic by its standard error. Now recall the key thing that determines the size of the standard error of a statistic. Recall that the standard error of a statistic is determined primarily by your sample size. If you have a large sample, well, then your standard error of a statistic is going to be a very small value. And if you have a small sample, well, then your standard error of a statistic will be a very large value. So that means the t-value is something that's to a large extent determined by your sample size. And this is a very good way of understanding what a t-value is, and a very good way of understanding what it means when we get significant results. So if we do a study and get significant results mean that the sample was large enough to reject the null hypothesis. The sample was large enough to conclude that you have discovered some non-zero effect. Recall that significance testing is a process we use to address that question of whether results for a study might be explained by chance. Whether the results of a study might just be some random chance fluke finding. So when we do significance testing, if I get a significant result, it means I'm concluding that my sample size was large enough to conclude that my results were not due to chance, that my results are not some random chance fluke finding, and that I have really discovered some non-zero effect, and my sample size was large enough to make that conclusion. Now, one thing to keep in mind when we're doing significance testing is that this whole process involves making a dichotomous decision between just two options. When we're doing significance testing, we only have two options, no more, no less, and there's no in between. So one option is that I claim to have discovered something, and another option is that I refrain from claiming to have discovered something. Either I claim to have discovered something, or I don't claim that I discovered anything. And with significance testing, those are my only two options. Sometimes when people do significance testing, say they get a p-value of 0.06. And 0.06, note that would be not significant because that's not less than 0.05, but it comes kind of close to 0.05, and people are often tempted to say things like, oh, this came close to being significant, or it was almost significant, or it approached significant, or it's marginally significant. But when we're doing significance testing, the logic of this procedure does not allow us to say things like that. Because when we're doing significance testing, our only options are either to claim to have discovered something or to refrain from claiming to have discovered something. The language we use when we're doing significance testing is a little bit like how we would talk about whether someone was pregnant or not. We would not say someone was marginally pregnant or approaching being pregnant or almost pregnant or partially pregnant. And in the same way, we would not say that results are partially significant or marginally significant or approaching significance. This procedure is one that requires us to do one thing or another. There's only two options. Either we claim to have discovered something or we refrain from making that claim. And that's the only options we have when we're using this procedure of significance testing. Also, keep in mind the fact that significance testing is not effect size. So with significance testing, we're addressing that question of whether our results could be explained by chance and whether our sample was big enough to conclude that our results were not simply due to chance and that we've discovered some non-zero effect. But when I claim results are significant, I'm simply claiming that the effect was not zero, and I'm not saying anything about how big the effect was. So significance testing is not effect size. These are two separate issues, two separate questions, and when we do significance testing, we're not saying anything about effect size. Now, notably, if you're doing a study and trying to investigating something, and the thing you're looking at has a big effect size, that makes it easier to get significant results. And if you're investigating something that has a small effect size, that makes it harder to detect significant results. Notably, the size of the effect size for your statistic in your formula will determine how easy it is to find significant results or not. But the key thing that significance testing is doing is determining whether your sample was big enough to detect a non-zero effect. And when you say results are significant, you're simply saying the effect was not zero, and you're not saying anything about effect size. And when you look at results from significance testing, you can't use those results just by themselves to draw conclusions about effect size. A significant result does not mean you have a big result. It simply means you have a non-zero result. Now, there are alternate approaches. You might be thinking, well, I don't like being forced to make this dichotomous decision, and this idea of just claiming whether the result is zero or not seems rather simplistic. Couldn't we use something more complex? One alternate approach to addressing this issue of sampling error is to do something called confidence intervals. And we'll be looking at confidence intervals later on in this course. So I could do a study where, say, I calculate an effect size, and then I use my standard error of my statistic. I could use the standard error in a formula that would allow me to calculate a confidence interval around an effect. So say, for example, I calculate a difference between two means, and say my difference, say I have two means that are 5 units apart. And then I could try to do a confidence interval where I would say I am 95% confident that the true difference between means maybe is somewhere between a 3 and a 6 or something like that. So I can try to do a confidence interval where I'd say I'm 95% confident that the true parameter is somewhere between these two values. We'll be talking about this issue of confidence intervals later on in this course. And note that this is an alternate approach to addressing the issue of sampling error. It's an alternate way of doing inferential statistics. It's an alternate way of addressing that question of whether results could be explained by chance or not. And in many ways, doing confidence intervals is a better approach because it gives us more information. If I do a confidence interval, I'm going to say, I'm 95% confident that the true population parameters may be somewhere between here and here. And that gives me some idea where I think that parameter is. It actually gives me some idea of effect size. Whereas if I'm doing significance testing, I'm just saying, if it's significant, I'm just saying the effect is not zero. So if I do significance testing, I just say the effect is not zero. That's not as much information as if I do a confidence interval and say the effect is somewhere between this value and that value. And we'll be talking about confidence intervals a little bit later on, but we're not going to spend a whole lot of time on confidence intervals, largely because although confidence intervals give you more information, they're not used that much. And by and large, almost everyone in research uses significance testing as the primary way of dealing with sampling error. And so because this is the tradition, that's what everyone does. It's the thing you need to know how to do if you're going to understand research. It's the thing you need to be able to do if you're going to publish research or do research. So because significance testing is by far the dominant way of dealing with this issue of sampling error, that's the approach we're going to focus on in this class. But keep in mind, it's not the only way. We could do this thing of calculating confidence intervals, and that would be another approach we could use for dealing with issues of sampling error and the fact that we have a result from a sample and we want to know how close the result from our sample actually applies to the true population parameter. I also want to clarify a few important points about the null hypothesis. So recall that the null hypothesis is that in the population, the effect is zero. So for example, if I do a study and I investigate a difference between two groups, the null hypothesis is that in the population, there's no difference between the groups and the mean difference is zero. Or if I do a study and I plan to calculate a correlation, the null hypothesis is that in the population, the correlation is zero and there's no relationship between the two variables in my study. And the key thing to keep in mind here is that the null hypothesis is that the effect in the population is exactly zero. No more, no less, exactly zero. And zero is an infinitesimally small point on a number line. So when we say that the null hypothesis is that the effect in the population is zero, that's proposing that the effect in the population is an infinitesimally small point on a number line. Here I have a number line, and for example, I'll draw a mark right here at the point 0, and I'll draw another mark right here at the point 4. And note that any 2 points on this number line, I could always divide it in half. So here's 0 and 4. I could divide that in half and get a 2. I could divide that in half and get a 1. I could divide that in half and get a 0.5. I could divide that in half and get a 0.25. And we could go on and on and on, dividing these 2 points in half over and over and over again, and we could do that infinitely. So 0 on a number line is an infinitely small point. So, for example, say I was looking at the difference between men and women and how much they like blue-footed booby birds. And say in the population, if somehow I were able to determine what the true population parameter was, and say the difference between men and women was this. I got an effect, a difference between two means, for example. Say the difference between men and women was 0.000000. I've lost track of how many zeros. 0.000001. A tiny, tiny, very small value there. But if note that value there, that is not zero. So if this is our effect, if it's 0.0000, a whole bunch of zeros, 1, then the null hypothesis is false. That effect is not exactly precisely 0. It's not that infinitesimally small point on a number line of exactly 0. And if the true population parameter is not that infinitesimally small point of 0 on a number line, then your null hypothesis is false. So even if your effect is an incredibly small value, if it's not 0, then the null hypothesis is false. And so with that in mind, we can note that probably the null hypothesis is probably never true. In reality, there's probably not anything we would study where if we assessed the entire population and calculated the effect, maybe it's a difference between two means or calculated a correlation, whatever the effect was, it's probably rarely ever true, maybe never true, that if we calculated that true population parameter, we would find that the effect was exactly, precisely 0. So you might wonder, well, what's the whole point doing significance testing if, from a logical point of view, the null hypothesis is probably never really true? And the answer is this provides a good threshold for us, because recall what we're doing, we're simply saying when we do significance testing, was our sample large enough to reject the null hypothesis? And this essentially provides a threshold. It says that if we do a study and our sample was not large enough to reject the null hypothesis, we should just stop there and not make a claim about anything. So an ability to reject the null hypothesis is kind of like a minimum threshold. It's something that the scientific community has agreed upon, that you need to be able to at least reject that null hypothesis before you can make a claim to have discovered something. And if you can't at least reject the null hypothesis, there's too much risk that your results might simply be due to random chance findings, and therefore you should shut up and not say anything. So even though on one hand the null hypothesis is probably almost never true, the rationale for using this procedure is the idea that it's a hurdle. You should at least be able to reject that null hypothesis before you're allowed to make claims to have discovered anything. Now, along this line, note that this means that we cannot ever actually test a null hypothesis. Every now and then someone does a study, and actually sometimes I have a student or a graduate student that proposes a research study, and they propose different hypotheses that they want to test, and sometimes they say, my hypothesis is that there's going to be no difference between two groups. Maybe they say, my hypothesis is that there's no difference between men and women and how much they like blue-footed booby birds. Well, you can't propose that as your hypothesis. You cannot logically propose the null hypothesis as a hypothesis you want to support in your study, because the null hypothesis is that the effect is an infinitesimally small point on a number line, and you can't get results that would show that your null that would support the idea that the true population parameter is this infinitesimally small point. Because if I did a study and got a very small result, well, it might be a result that's close to the null hypothesis, but that doesn't support the null hypothesis that the effect is this infinitesimally small point on a number line. So keep in mind, we cannot ever actually test the null hypothesis. We assume the null hypothesis before we start a study. So the null hypothesis is something that we assume before we do a study, but we can't do a study that would test the null hypothesis to see if it's true or not, because we can never determine whether the true population parameter actually is some infinitesimally small point on a number line. And then finally, on this page here, I want to note that non-significance should never be taken as support for the null hypothesis. Sometimes people do a study and they get results that are non-significant, and then they interpret that as saying, oh, I guess there must be no effect between these variables. Maybe they do a study looking for a difference between men and women. Maybe it's looking at a difference between men and women and how much they like blue-footed booby birds. And they get a non-significant result. And then they may be tempted to say, oh, this gives support for the idea that there's no difference. My results show that there's no difference between men and women in how much they like blue-footed booby birds. And that is a bad way to interpret results. If you get non-significant results, it's not support for the null hypothesis. It just means you failed to detect anything. And just because your sample was too small to detect anything doesn't mean there's nothing there to detect. So, for example, say someone was going to do a study, and say they were going to look at a telescope and look for the moon. I've got a picture of a moon up here. So say someone was going to look at the moon, and they looked through their telescope, and someone looked through their telescope to look at the moon, and they looked through their telescope and they didn't see the moon. They looked and said, well, I don't see the moon there. I have failed to detect the moon. So should we take that as support for the idea that the moon doesn't exist? Would we take that as support for the idea that there is no moon? Well, no, that would be silly, because a simple failure to detect something doesn't mean it doesn't exist. Just because you didn't see the moon when you looked through the telescope doesn't mean it doesn't exist, and it's not support for the idea that it doesn't exist. I don't know, maybe it was cloudy out. Maybe the moon wasn't where you were looking. Maybe you had your lens cap on. There could be all kinds of reasons why you might look through a telescope and not detect anything. So if you look for a result and you fail to detect it, that's not evidence that that thing doesn't exist. It just means you failed to detect it. It means if it did exist, you failed to detect it. So if you get non-significant results in a study, that should never be taken as support for the null hypothesis. So it means the null hypothesis is something we simply assume, but we never test it. We can't prove it. We can't test it. And if we get non-significant results, that's not support for the null hypothesis. It's simply something we assume, but a non-significant result just means we fail to reject it, but that's not the same as supporting it. Non-significant results should not be taken as support for the null hypothesis. So those are some important things to keep in mind about the null hypothesis. And that brings us to a final song. Here is a song for significance. And the lyrics to this song define the important things to know about significance. So they say, when the p is less than 0.05, I call it significant because I derive the sample was big enough to make me a hero, and now I can claim the effect is not zero. So when we do significance testing, we calculate a p-value, and if our p-value is less than 0.05, we call our results significant. And when we call results significant, it means that our sample was big enough to conclude that we have a non-zero effect. So that's what significance testing is. And as always, I encourage you to listen to the song and to sing along and to see if you can sing it without looking at the words before I'm done. So here is the song for significance. Now, up to this point, all my examples of significance testing have involved calculating a t-value. And I mentioned that a t-value can be called a test statistic. That is, it's a statistic that has a known distribution if the null hypothesis is true. And because it has a known shape or a known distribution when the null hypothesis is true, that means we could calculate a t-value and then determine the probability of that t-value if the null hypothesis is true. Now, as it turns out, there are some other statistics that also function as test statistics. There's other statistics that also have a known distribution or a known shape when the null hypothesis is true. One other test statistic is called an F statistic, and another example is something called a chi-square. That's the Greek letter chi that's squared, so chi-square. So T and F and chi-square, those are all examples of test statistics. They're all statistics that have known distributions, a known shape of a distribution if the null hypothesis is true. So we can do a study and calculate a t, or calculate an f, or calculate a chi-square. We can calculate a test statistic, and then because these statistics have distributions with a known shape if the null hypothesis is true, we can determine the probability of those statistics. Now, these are things that we would use different statistics depending on what our situation is. For example, later on in this course, I'll be talking about how we would calculate a t-value if we have something I'll call a focused question, and we would calculate an f-value if we have something called an omnibus question. And I'll be talking more about that later. For right now, just keep in mind the fact that these are all different examples of test statistics. These are all statistics that have known distributions if the null hypothesis is true. And so that means we could calculate these statistics and then determine the probability of these values if the null hypothesis is true. And by the way, this class will be dealing quite a bit with t-values and f-values. We're going to deal with those quite a bit. For this class, we're not going to do a whole lot with chi-square, but that is another example of a test statistic. Notably, both an f distribution and a chi-square distribution, these are distributions that look different than a t distribution. They take on a different shape. Recall that a t distribution has a shape that comes very close to a normal distribution, and if you have large samples, it's identical to the normal distribution. So it's that symmetrical bell-shaped curve is the shape of a t distribution. In contrast, both an f and a chi-square are going to be skewed distributions. What we're looking at here is an f distribution. So this would be a situation where if the null hypothesis is true, I get a sample of people and calculate an f value, and get another sample of people and calculate an f value, and I replicate my study over and over an infinite number of times. And if the null hypothesis is true, then the f distribution would take on the shape that you're looking at here on the screen. And note that's a skewed shape to it. It's not that symmetrical bell-shaped curve that we saw for the normal distribution. It's this skewed shape. So this is what an f distribution looks like. And here's what a chi-square distribution looks like. It's a little different from an f, but it's also a skewed distribution like the f. So both the f and the chi-square, those are both skewed distributions. The t distribution is a bell-shaped distribution that comes very close to the shape of a normal distribution. But all three of these are test statistics. All three of these distributions have a known shape if the null hypothesis is true. So all three of these statistics can be used in significance testing to determine the probability of results under the assumption of the null hypothesis. And that is everything for Part F of Unit 2.